Chapter 18.5 The Kruskal-Wallis One-Way ANOVA. In Chapter 11, you learn about the analysis of variance procedure or ANOVA, which allows us compare the means of three or more population. This is a parametric test that relies on the following assumption. The population are normally distributed. The population have equal variances. The data are at least at the interval level of measurement. If these assumptions are not valid, the ANOVA procedure will not provide reliable result. The Kruskal-Wallis test is a non-parametric procedure that allows us to determine if a difference exists in the median of three or more population. The beauty of this test is that it does not rely on any assumption about the probability distribution or require equal variances among the population. The following are the only requirement of the Kruskal-Wallis test. The level of data measurement must be at least ordinal. The size of each sample must be 5 or more. However, like other non-parametric procedures we've discussed, the Kruskal-Wallis test have less power than the ANOVA test. The Kruskal-Wallis test begins by combining all of the data from the samples and ranking the values from low to high. The test statistic for the Kruskal-Wallis test, or H, can be found using equation 18.9, where H is the test statistic for the Kruskal-Wallis test. Summation of R1 is the sum of the ranks from sample 1. K is the number of population being compared. N1 is the size of sample 1. Nt is the total number of observation from all of the samples. Let's use the following example to examine this procedure. Suppose the American Association of Retired Persons, or AARP, would like to determine if the median amount of money people have saved in their 401k retirement account is different for different age groups. Sample data from each age group was collected and is shown in Table 18.23. This data can also be found in the Excel file retirement balances.xlsx. The following step demonstrate the Kruskal-Wallis test using alpha equal to 0.05. Step 1. Identify the null and alternative hypothesis. Like the ANOVA procedure from Chapter 11, the null hypothesis always states that there is no difference among the median of the population being tested. Therefore, the alternative hypothesis will state that there is a difference. For example, null hypothesis, there is no difference in the median 401k balances among each group. Alternative hypothesis, there is a difference in the median of 401k among each groups. Step 2. Sort all of the data values from low to high and rank them. Table 18.24 shows the combined data from all three samples sorted from low to high values along with their corresponding age groups. The yellow highlighted values in the table correspond to the 50 to 54-year-old age group. The blue highlighted values correspond to the 55 to 59-year-old age group, and the green highlighted values to the 60 to 64-year-old age group. Step 3. Sum the rank for each sample. Next, we sum the rank for each sample using the information provided in the table. For example, if we define sample 1 as the 50 to 54-year-old group or yellow highlights, then R1 is the sum rank for these balances. Summation of R1 is equal to 1 plus 6 plus 7 plus 9 plus 13 equal to 36. Defining sample 2 and sample 3 as the 55 to 59 blue highlight and 60 to 64 green highlight year-old group respectively, we get summation of R2 equal to 70 and summation of R3 equal to 65. Step 4. Determine the test statistic for the Kruskal-Wallis test H. Using N1 equal to 5, N2 equal to 6, N3 equal to 7, and N total equal to 18, we can now calculate the test statistic using equation 18.9. H is equal to 58.93 minus 57 equal to 1.93. Step 5. Determine the critical value for the Kruskal-Wallis test H. The test statistic shown in equation 18.9 follow the chi-square distribution with k-1 degrees of freedom. These critical values can be found in Table 8 in Appendix A, which can be found in the print version of the textbook. Using alpha equal to 0.05 with k-1 equal to 2 degrees of freedom, H alpha is equal to 5.991. Step 6. Compare the test statistic H to the critical value H alpha. Table 18.25 summarizes the decision rules for the Kruskal-Wallis test. Because H is equal to 1.95 is less than H alpha equal to 5.991, we fail to reject the null hypothesis. Step 7. State your conclusion. Because we fail to reject the null hypothesis, AARP cannot conclude that the median 401k balances for the three age groups are different. At this point, the logic of the Kruskal-Wallis test can be explained. First, let's recognize that the sum of all 18 ranks equal to the sum of 1 to 18 or equal to 171. This quantity also equal summation R1 plus summation R2 plus summation of R3 equal to 171. If there were a difference in the median balances of the 401k account among the three populations, the null hypothesis is rejected. We would expect one sample to have an average rank that is much higher than the average rank of the other samples. This would cause another sample to have an average rank that is lower compared to the other. This occurs because sum of all 18 ranks must equal 171 in the AARP example. A large value for summation of R1 square in equation 18.9 causes the value of the test statistic to be relatively large, which increases the likelihood of rejecting the null hypothesis. Looking at the opposite scenario, if there were no difference in the median 401k balances among the three groups, or the null hypothesis is not rejected, we would expect the average rank of all three samples to be fairly close to one another. This would occur because each group would contain about the same proportion of low, medium, and high 401k balances. Under these circumstances, the value of the test statistic would be relatively small, which increases the likelihood of failing to reject the null hypothesis.